Welcome to the Deep Dive, where we cut through the noise and get straight to the core of complex topics. Today we're tackling something that sounds, well, incredibly technical, but has profound real-world implications. How we figure out true cause and effect, especially when the data is just really messy. We're diving into excerpts from a fascinating chapter called Applied Causal Inference, powered by ML and AI, by Victor Chernozhukov and his co-authors. Now, this material can be dense, but our mission here is to extract those powerful, sometimes surprising, nuggets of knowledge, giving you a shortcut to being truly well-informed about how machine learning is, frankly, revolutionizing our ability to establish robust causal links.
That's absolutely right. For, well, centuries, really, distinguishing true cause and effect from just, correlation has been a fundamental challenge. Across countless fields, medicine, economics, you name it. This deep dive shows how modern machine learning tools aren't just improving things slightly, they're fundamentally transforming our ability to get reliable answers, overcoming many limitations of ARCR methods.
Okay, so let's unpack this right away. At its heart, what are we trying to achieve with causal inference? And then how does this double machine learning DML fit into that ambitious goal?
Right. So causal inference is fundamentally about answering those critical what-if questions. What if we change X? What genuinely happens to Y? It's the absolute bedrock for making smart policy decisions or launching effective medical treatments or even crafting impactful business strategies. Now, DML, double machine learning, it's a powerful statistical method that marries the best of machine learning with, let's say, classical econometrics. The core idea is actually brilliantly simple. Use machine learning to expertly filter out what we call nuisance functions.
Okay, nuisance functions. That definitely sounds like something you'd want to get rid of.
Exactly. Think of these nuisance functions as all the complicated background noise, or the confounding relationships between variables that aren't the main causal effect you're actually interested in, but which, if you don't handle them correctly, can completely bias your results. It's like trying to hear one specific voice in a really crowded, noisy room. DML uses ML to expertly clean up that room, predicting and then effectively subtracting all that background chatter, all that noise. By doing this really flexibly, DML allows us to then focus intensely and accurately on estimating just the causal effect of interest, giving us truly valid statistical insights.
That's a powerful way to put it. So if DML can expertly filter out the noise, it sounds like it's particularly useful when things are inherently messy, or maybe when we're dealing with indirect influences, like in situations involving these things called instrumental variables. That word really shines.
You've hit on it perfectly, yeah. Instrumental variables, or IV, come into play when you have what's called an endogenous variable. Essentially, it's a chicken and egg problem.
Yeah.
Right. This is a variable whose variation is itself influenced by or correlated with the outcome you're studying in a way that just confounds a simple cause and effect analysis. An instrument acts as a proxy or maybe a clever lever, something that influences your problematic endogenous variable. But crucially, it only affects your ultimate outcome through that endogenous variable. And DML really helps estimate causal effects in these incredibly complex settings, even when the relationships aren't neat and linear.
Okay, can you give us a real-world example where this kind of lever was needed and how DML improved the understanding?
Sure. A classic, really influential example comes from Acemoglu, Johnson, and Robinson, AJR, back in 2001. They studied the effect of institutions on economic growth. So here, the outcome variable Y was the logarithm of GDP per capita for about 64 countries. The endogenous explanatory variable D was an index measuring protection against expropriation risk, basically a proxy for how strong a country's institutions are. And the challenge is clear, right? Strong institutions might lead to higher incomes, but maybe higher incomes also let you build stronger institutions. A classic simultaneity problem.
The chicken and egg.
Exactly. So to cut through this, AJR used a fascinating instrumental variable, Z, historical mortality rates for early European settlers. Their argument was pretty clever. Early settlers established institutions based on how deadly the environment was for them. Higher mortality meant less settlement, worse institutions, basically. And these institutions, they argued, were persistent, they stuck around, and crucially, early settler mortality influenced modern GDP only through its lasting effect on these institutions. They also included control variables, X, like distance from the equator, continent dummies, acknowledging that geography could also be a confounding factor.
Right, geography matters. So how did DML enhance this already clever approach? What did it add?
Okay, this is where it gets really interesting. AJR, in their original work, had to make an assumption. They assumed that geography's confounding effect was, well, linear.
Just a straight line relationship.
Yeah, pretty much. But DML allows us to completely relax that assumption. Instead, it uses powerful ML methods, think random forests, to learn an unknown flexible function of distance and continent dummies. This gives us a far more flexible and potentially much more accurate way to control for geography's influence. And when DML was applied here, the results showed consistently large and positive estimates for the effect of institutions on output. For instance, one coefficient was 0.86 with a standard error of 0.33. Now, that's somewhat smaller than AJR's original baseline estimate, which was 1.10, but they're qualitatively very similar. Still indicates a strong positive effect.
Wow. So the surprising takeaway here is that DML didn't just confirm the original finding. It actually confirmed it under a much more realistic, less restrictive assumption about how geography affects things.
Precisely. It adds robustness.
That's incredibly powerful, moving beyond those simple linear assumptions to uncover maybe deeper truths. Building on that, if DML can help untangle effects on something as massive as national economies, what about zooming in? Can this sophisticated tool help us understand very specific impacts, say, on a particular subgroup of people? That's where this concept of local average treatment effects, or LATE, comes into play, right? And it seems like another area where DML really shines.
Absolutely. LATE focuses on estimating the causal effect for a very specific subgroup, often called compliers. These are the individuals whose treatment status, whether they get the treatment or not, is directly affected by the instrument. It's frequently used with binary choices like, did someone participate in a program or not? As the Nobel laureate Guido Imbens famously quipped, better late than nothing.
Yeah, right.
Implying that getting a precise causal effect for a specific group, even if it's not everyone, is much better than getting a biased or meaningless average effect for the whole population.
Give us an example of this in action, maybe something relatable to our daily lives.
Okay, we can look at the effect of 401k participation on net financial assets, a topic relevant to many people. Here, the outcome, Y, is an individual's net financial assets. The endogenous treatment, D, is whether someone actively participates in a 401k plan.
Why endogenous? Doesn't the company just offer it?
But even if offered, the choice to participate likely depends on other factors, things like financial literacy, maybe self-discipline, income levels, all of which also directly affect your assets, right? So if you just compare participants to non-participants naively, you're likely not getting a clean causal effect of the 401k itself.
Okay, makes sense. So what's the instrument?
The instrument, Z, used here is 401k eligibility. Are you even allowed to participate? Eligibility is generally considered a valid instrument if it influences participation, which it clearly does, but only affects your assets through that participation decision. Now, when DML was applied here, researchers used different machine learning methods to estimate those nuisance functions we talked about, and the results were quite revealing. One method, Lasso, actually performed pretty poorly. It yielded a negative estimate, NYSHA 152151, with a massive standard error of 19,243.
Whoa, 19,000. So what does imprecise mean here practically?
It means the margin of error was so huge, plus or minus over $19,000, that the actual effect could have been anything from a big negative number to a big positive one. It basically told us nothing reliable, which, by the way, shows that even within the world of ML, choosing the right tool for the job is critical.
Good point. So what worked better?
Well, other more flexible methods like random forests, trees, and boosting performed much better. They returned consistent and positive estimates. For example, an ensemble method, which is like a combination of methods, gave an estimate of around $11,471 increase in assets with a much more reasonable standard error of 1623. Now, what's really key here is that these DML results are broadly consistent with estimates from earlier, simpler linear IV models, which were around $13,102. But notice they are somewhat smaller. We call this attenuation.
Attenuated, meaning less strong.
Yeah, slightly smaller effect size. And this attenuation is actually a surprising and important insight. It suggests that those simpler linear models used before might have actually overestimated the true effect, perhaps because they weren't flexible enough to capture all the complex ways other factors influence asset growth alongside 401k participation. DML, with its flexibility, seems to be giving us a more accurate, perhaps more conservative, but ultimately more truthful picture of the 401k's impact for those induced to participate by eligibility.
So the really powerful takeaway here seems to be that DML helps us get a more nuanced, potentially more accurate picture of a specific causal effect, even for these very precise subgroups. It does this by letting the machine learning untangle all those complex underlying relationships that traditional methods might miss or maybe oversimplify. Okay, and on that note, let's turn our attention to another major headache in causal inference, weak instruments. We've talked about these levers or instruments that unlock causal effects, but what happens if your lever is, I don't know, flimsy, barely related to the thing it's supposed to influence? How does DML help there? Because this sounds like a really pervasive problem in real data.
Oh, it is. This is a truly critical point, and it's surprisingly common. Weak identification, or weak instruments, simply means that the statistical connection between your instrument, your z, and the endogenous variable, your d, is very small, often statistically close to zero. Think of it this way. If you're trying to pull a really heavy object with a very thin, stretchy piece of elastic.
Right, the elastic just stretches, the object barely moves.
Yeah, exactly. The elastic barely moves the object, and you can't really tell if you're actually having an effect or just, wiggling the elastic. When this happens in statistics, traditional IV estimates can become wildly unreliable. They can be biased, their distributions look strange, and crucially, their confidence intervals, which are supposed to tell you the range of uncertainty, might not truly reflect the uncertainty at all. The statistical assumptions they rely on simply break down.
So your conclusions could be completely invalid.
Potentially, yes. Making inferences can be very risky.
So if traditional methods are giving us completely unreliable answers with these weak instruments, is there anything DML can actually do to give us a trustworthy result? Can it fix this?
Absolutely. This is where DML truly shines, almost like a statistical truth serum for these tricky situations. It offers what's called weak identification, robust inference. Now, instead of relying on those standard, often optimistic, asymptotic assumptions that basically require strong instruments, DML uses a different statistical approach. Specifically, it often relies on methods related to something called the Anderson-Rubin statistic, or similar approaches like the C-test statistic you mentioned. The beauty of these methods is that their validity doesn't hinge on the instrument being strong. It essentially builds a confidence region, a range of plausible values, by finding all the possible values for the effect that cannot be statistically rejected based on the data. Even if the instrument is weak, this gives you a rock-solid, much more honest range for your estimate, even when your data connections are faint or noisy.
Okay, let's make this concrete. Can we revisit the AJR example, the one about institutions and economic growth? How does this robust approach change things there?
Excellent idea. It's a perfect illustration. So when we re-examine the AJR study using DML, specifically with random forests to form the residuals needed for the analysis, the t-statistic measuring the strength of the instrument, how strongly settler mortality predicts institution quality after accounting for controls, was approximately 2.
2? Okay,
Yeah.
how does that compare to, standard practice?
Well, it's much lower than any conventional rule of thumb safety threshold for instrument strength. People often talk about needing an F statistic over 10, which corresponds to a t-stat over roughly 3.16. Some even argue for higher thresholds.
So 2 is definitely in the weak zone.
Unquestionably. It emphatically confirms we have a weak instrument problem here. Now, if we ignored this and just used the usual, often too optimistic Gaussian approximation for inference, the 95% confidence interval for the effective institutions on output was 0.20, 1.52.
Okay, so between 0.20 and 1.52.
Right. But now, using the DML weak IV robust method, the 95% confidence region shifted. It became 0.282.
0.2 to 2. Okay, what's the significance of that shift?
What's truly fascinating, and potentially quite important economically, is the difference in the lower bounds, 0.20 versus 0.28. The usual, less reliable interval couldn't rule out an effect size smaller than a 20% increase in GDP per capita for a 1-unit increase in institution quality. But the robust DML interval could confidently rule out all effect sizes smaller than 28%.
Ah, so it gives you more confidence that the effect isn't that small.
Exactly. That 8% difference in the minimum plausible effect size from 20% to 28% is significant when you're talking about national income levels. Given that we know we have a weak instrument, the robust confidence interval 0.282 is the one you absolutely need to rely on. It prevents you from making decisions based on potentially misleadingly narrow or just plain wrong estimates of uncertainty.
This really highlights the critical role DML plays, doesn't it? Ensuring that our findings are trustworthy, especially when the underlying data relationships are challenging and subtle. It provides a more accurate, perhaps more conservative sometimes, but ultimately far more honest estimate of the uncertainty, which is just vital for making genuinely good decisions based on data.
Precisely. To sort of summarize, this deep dive really shows how DML, by powerfully leveraging machine learning's incredible flexibility, offers remarkably robust and reliable ways to estimate causal effects, even in the thorniest situations. It helps us expertly navigate complex scenarios involving instrumental variables. It lets us extract precise insights for local average treatment effects on specific groups. And critically, it helps us overcome the pervasive and often invisible issue of weak instruments. This means getting to more trustworthy insights from data insights that were previously obscured, biased, or maybe simply unattainable.
And for you, the learner, this means a more profound understanding of how these cutting-edge methods are refining our ability to discern true cause and effect. It gives you a real shortcut to being well-informed, but with the surprising facts and the depth, you really need to truly grasp these important advancements. So, thinking beyond this chapter, given how crucial it is to establish true cause and effect relationships in everything from economic policy to medical treatments, what other fields, maybe outside the usual suspects of economics and healthcare, could be truly transformed by systematically applying these robust ML-powered causal inference methods, especially where traditional approaches struggle with those subtle, weak connections? What's the next frontier for this kind of rigorous analysis?